lot of facts. Now we got to save the best for last, the interpretation, the theory, whatever you like to call it. And our first speaker is Maarten Volonteri of the Institute of Astrophysics, who will tell us about the first black holes.
Keep introducing her. Some people need to use their own laptop. It's kind of okay. Well, let's see.
Thank you very much. And it's a real honor to be here and celebrate the discovery of quasars. And the discovery of quasars was really when they were recognized as cosmological objects. And today I would like to discuss with you when this cosmological inference is brought to its extremes. So the first black holes and quasars at high redshift. In fact, at this point, we have heard this already this morning. Quasars have been discovered to very large distances, corresponding to a very young age of the universe. And these quasars can help us put constraints on how and when black holes form, so the process of black hole formation, how fast they grow, how galaxies can feed black holes, and what is the effect of feedback from black holes on their environment. And I would like to discuss a little bit of this with you today. So let me just show you here where we stand. The current redshift holder for the quasar farther away from us is ULAS 1120, that, as discussed already, has a redshift of 7.1. This corresponds to an age when the universe was only 750 million years old. The estimate for the mass of this black hole, however, is about 2 billion solar masses. If we put this on the same scale as black holes today, this is the black hole sigma relationship that we have seen already a couple of times. This black hole would sit out there. So is as massive as the largest black holes today, but when the universe was much younger. Now, we can use this particular quasar as an example to learn a few lessons about the early growth. Let's start by assuming, very conservatively, that accretion occurs always below the Reddington limit. Now, this is very convenient because you can express the mass growth in a very simple way. You start from a black hole seed with a mass m0, and you grow exponentially as a function of time with only two parameters here. One is the relative efficiency, epsilon, which is typically related to the spin of black holes, and is between 6 and about 30%. And the Reddington ratio here that we can assume for the moment to be 1. This simple equation can be recast in terms of growth time from the initial mass of the seed, whatever it may be, to the mass that we see. So for ULAS J1120, the mass is about 2 billion solar masses, and we know that the growth time must be equal or less to the age of the universe at that time. Now, this means that we have a very, a very strict constraint. So if the age of the universe is 750 million years, the ratio between the growth time and the age of the universe is expressed as this ratio here. First, you see that there is only a logarithmic dependence on the ratio between the black hole masses. And in the end, we have just all these expressed as a function of these three parameters. So we can use this particular object to have an idea about how difficult or easy it is to grow it as a function of the black hole initial mass, the typical radiation efficiency, and the typical Reddington rate. The typical Reddington rate, you can imagine here in this context as being the efficiency, the ability of the black hole to be fed by its host galaxy. So, as I said, this is an object which is very far away from us, so we have to go into cosmological context and put this into what we know about the evolution of the universe. So what we can look at is a cosmological simulation that shows the evolution of galaxies from early times to today. Now, this is dark matter only. It's a very simple way of looking how gravity operates. But when we want to study things in more detail, we can go and select a patch of this cosmic web. You see here the peaks, the filaments, and the voids, and try to study it at much higher detail. So let me select a region there that is similar to the Milky Way today, and go to a higher resolution simulation, which follows in much more detail the physics that we see. So here you see a simulation starts at early times and goes on. The color coding is that green is gas. In this particular case, you see the gas permeating the filaments among galaxies. And here you see the first proto-galaxies. These are the early times. Stars, when they form, are blue, and they become redder with time, as we know they become. So here you start seeing this early universe when galaxies were small. We're in a lambda CDM universe. And here we see the establishment of a galaxy really like our own Milky Way. What we want to study within this evolution of galaxy formation is the processes that form first and grow black holes in these galaxies. We may imagine that some, if not all, of these proto-galaxies host black holes. And we know that the galaxy today, there was a major merger. For the Milky Way, this was quite a long time ago. This is about redshift 2, and at this point, our favorite galaxy is just growing back its disk through a cosmic web feeding gas. And you see here its little bulge. And in this bulge, we expect there is a black hole. For the Milky Way in particular, we know that there is a black hole, about 4 million solar masses, but we want to know how common that is and what are the processes that grow these black holes. Now, I will stop this beautiful simulation that shows our own galaxy, and I will take a step back in time. Let's go back to one of the proto-galaxies and try to find ways that the gas and stellar content of these early galaxies can form a black hole in the center. And this black hole will be the seed upon which supermassive black holes grow. Now, let me start by showing you a simple diagram. Here, I will discuss with you only 3 pathways to form black holes. But in reality, if you go to see this paper by Maarten Schmidt, 1978, all these pathways and more were already discussed. So, like for quasar discovery, we are discovering over and over again black holes and ways of forming black holes, starting from this early work. So here, the idea is to take a proto-galaxy. We are going at very high redshift, so galaxies were a bit simpler than today. You can imagine them big as a ball of dark matter filled with gas. What can happen to this gas to form a black hole at the end point? As I said, I will describe only 3 mechanisms to form black holes. One that relies on the first generation of stars, one on gas dynamical collapse. Very often this is called direct collapse, if you have heard it. And the third one relies on stellar dynamical collapse, the effect of stars on each other. I'm not partial to any of these mechanisms to start with. I'm partial to the physics in it, in the sense that I like the fact that there is interesting physics in there. But unfortunately, I will end by saying that we don't have a constraint on this yet, although we would love to. Okay, so let me start with pop-tree star remnants. This is a very natural way of forming black holes. Why? Because we know that stars normally evolve, and the most massive ones end their lives as black holes. So the same pathways can be imagined to have happened at early times, with one difference, that early simulations of formation of the first stars, when I say first stars, I mean stars that formed when the universe was not enriched by metals yet, because you need stars to enrich the universe. And these stars were expected to be very massive. This is due to the physics of cooling happening at zero metallicity. And if you form stars that are pretty massive, say above 250 solar masses or so, their final fate at zero metallicity is to directly collapse into a black hole with a mass of order about half the mass of the star. So the mass loss in winds is much less than today. One problem is, were the first stars massive enough? We can look at different ranges of stellar masses and the black hole masses we expect from there. As I said, if the stellar mass is above about 250 solar masses, the final fate is to collapse into a black hole with a mass about half that of a star. So it's a tiny seed compared to the billion solar masses black holes that we observe at Redshift 6, but still is sufficiently massive probably to find the center of its galaxy. However, recent simulations revised the estimates for the mass of the first stars to be much less typically than this. So the peak of the IMF, the initial mass function, would not be skewed towards such large masses. What happens if you have lower mass stars? Well, if the mass of the star, again at zero metallicity, is between 150 and about 250 solar masses, there is no black hole left at all. You have a supernova, called a pure instability supernova, that completely destroys the star. Then you can go to even smaller stars, between 30, well, let's say less than 150 solar masses or so. In this case, again, you form a black hole. However, this black hole will be much smaller, will be much less than about 100 solar masses. Now, if you imagine now the fate of this black hole, if you have a small black hole immersed in a sea of gas and stars, it will be very hard for it dynamically to find the center of its halo, and it will be very hard for it to grow to larger and larger masses. In fact, if you go back to LAS J1120, for the typical radio efficiencies that you expect, the minimum mass that you need to grow to billion solar masses in 750 million years is about 300 solar masses. So I'm not saying that this is not a way to form the first seeds. I'm saying that probably the first massive, the supermassive black holes that we observe at Redshift 6 had a hard time growing if we start from small masses. But I will get back to it by the end of the talk, hopefully. Okay, so this is the first scenario, and we can call these small seeds that form in many galaxies. What happens if you have a galaxy that may actually create a larger black hole? This is what is typically called direct collapse, or gas dynamical collapse is what I prefer to use. In this case, we start again from a protogalaxy, a ball of gas immersed in a ball of dark matter, and a small fraction of galaxies we know are dynamically unstable. Dynamical instabilities mean that you can transport gas in at the expense of angular momentum. Now, if you have a deep enough potential well, you can start collapsing and getting gas to flow in through the effect of cooling, until eventually, at some point, you are stopped by rotational support at about parsec scale or so. This is not enough to form a black hole. You need to bring really this gas to very, very high densities in the very, very, very center. And that's where these dynamical instabilities come into place. They take the gas distributed in the galaxy and they're able to condense it in the very center. This is just an idea that is not new, and I will show here an early movie done in 2004, where you will see the establishment, maybe, of a dynamical instability. The movie is not working. I hope that the other work. Well, so let me move to 2013 instead. Okay. And show the establishment of one of these dynamical instabilities in another simulation. This was actually out last week on AstroPH. This is a high redshift protogalaxy, and here you can follow as a function of time. Notice the time in years, the collapse of this gas cloud to higher and higher densities towards the center. So you collect a large amount of gas in a very short time. What is key here is that this collection of gas happens on time scale shorter than star formation. The binding energy of one of these high-redshift galaxies is not much more than the energy in a supernova. So if you start forming supernova in this collapsing cloud of gas, you have lost all your efforts. You will blow away most of the gas, and you will never get to the densities that you want for black hole formation. So if instead you collect enough gas, you can form a supermassive star with some tweaks in it. You can call it supermassive star, quasi-star, depending on your favorite choices. But if you can form a supermassive star, given these very high inflow rates, typical inflow rates that you need are higher than about 1 solar mass per year in these small galaxies, you can create a massive black hole up to about 10 to the 5 solar masses. This is a very relatively large black hole in a small galaxy. Now, I talked about the formation of first stars. I talked about gas dynamical collapse. Let me just discuss a last scenario, which relies on the formation of a bunch of stars. So, stellar dynamical collapse. So, in this case, we can assume, again, the same galaxy, starting with gas and dark matter. But in this case, let us assume that this galaxy is not these unstable systems where you can collapse and condense several solar masses per year of gas in the center. Let's take a more normal galaxy. In this case, you have local dynamical instabilities, what typically we refer to as the Tumri instabilities. In this case, part of the gas is used for star formation, but part of the gas will flow into the center. You see here these bar-like structures. You therefore inflow much gas, several thousands of solar masses of gas in the very center. Now, if you increase the gas density in the center of a galaxy, you will lead to conditions where star formation is actually very efficient. You have a lot of dense cold gas. So we'll end up forming a dense cluster of stars in the very center. If you form a cluster of stars, the more massive ones will sink towards the center under the effect of gravity. They don't have much space left. Imagine this to be a cluster about 10 to the 5 solar masses within a few parsecs. When you run out of space, the stars will actually collide and merge and form a much more massive star. When the star reaches about 1,000 solar masses or so, well, at that point, it really depends on how many metals you have around. Suppose that you have the same process today. You form a very mass star. This star is an analog to a red giant. So most of the mass of the star will be actually lost in winds. But at very low metallicity, winds are much less effective. So a star which has initially about 1,000 solar masses in mass can eventually collapse into a massive black hole with a mass of about 1,000 solar masses. So as I said, this is just a selection of the pathways to form black holes. But the important point is that we can think of physics taking place in the first galaxies, creating black holes. And these black holes will eventually grow and explain the population of black holes that we see today. Now let me go back and put these black holes in the context of the first quasars. So what I was discussing was the growth of high redshift quasars and the relationship to the timescales that we have. Now, what do we see? You remember this equation, the growth time over the Hubble time as a function of these three parameters: the mass of the seed, the Reddington ratio, and the relative efficiency. Let me put some numbers here. For LAS J1120, we know that the mass is larger than about 10 to the 9 solar masses. We know the age of the universe, 750 million years. Let us assume an Reddington ratio of 1. And I just told you that the typical masses of the seeds that we get from this formation mechanism are between 100 and 10 to the 5 solar masses. Now, even assuming lower limits to relative efficiency, we still get that the ratio between the growth time and the Hubble time is at least 50%. What does it mean? It means that this black hole must grow at the Reddington limit for at least half of its lifetime, or for all its lifetime at the Reddington rate. Now, this is just a mathematical equation. The real difficulty is to have this happen in a physical system, with everything that happens in high-redshift galaxies. So the real problem is not a simple mathematical idea, but how does this black hole grow within the galaxies and regardless of what's occurring around them. In particular, the two things that I want to discuss with you is how can a galaxy feed a black hole? And the second is, if a galaxy can efficiently feed a black hole, what is the effect of the black hole on its environment? We know that the black holes, when they become AGN and quasars, emit enormous amount of energy and momentum. That's how they were discovered. But what is the effect of this energy momentum on the evolution of the galaxies, of the black holes themselves? So let me start with point A. How do galaxies feed black holes? And this was already discussed this morning, one of the ways that can increase the growth rate of black holes is through galaxy mergers. You see here a merger between two galaxies. We do know that galaxy mergers trigger gas inflows through losses of angular momentum. Now here, focus just on the luminosity of these central objects, the flickering of these objects. It's actually proportional to the luminosity of the black holes embedded in these galaxies. So we do see that, especially at pericentric passages, the black holes become very active and grow with time. So galaxy mergers are a good way of feeding black holes at very high rates. However, galaxy mergers are not occurring the whole time. And as I said, these high redshift black holes must grow pretty much for the whole time. So what are other options? One is simply that, and again, movies are not working, I'm sorry. Oh, okay, just slow. One other option is that the streams of gas from the cosmic web help replenish the gas in galaxies. So here what you're seeing is a simulation of the evolution of a redshift 6 galaxy. Here all the streams that you're seeing is gas coming from the cosmic web. And if I can go back. I would like to show you the effect of the quasar on the galaxy itself, but we will see that later. And let me just first quantify a little bit what I just said. So instead of taking these two things separately, the growth through galaxy mergers and the growth to cosmic streams of gas, let's look at their relative importance, at least in one black hole. So this is the history of a black hole in a galaxy which is much smaller than ULAS J1120. As you see here, the mass of the black hole is about 10 to the 6 solar masses at redshift 4, so it's a much smaller system. But we can still looking at its evolution. So here, purple is the black hole mass as a function of time. And we can divide the way the black hole grew in mass through the different avenues. So here, so first, we can look at how much mass came in through accretion of gas, and this is shown here in black. So this means that a large fraction of the black hole mass came through accretion rather than mergers. But let's subdivide it into into more clear ways. So here, blue is gas that came in from cosmic streams of gas and connected directly to the galaxy, being cold. Cold gas is very good to condense the center and feed black holes. Here you see a red curve. This is gas that has been shock heated before reaching a black hole, and you see here it's very difficult for this hot gas to feed black holes. And the final curve is shown here in green. This is the mass that was brought to this black hole through galaxy mergers. So when you have a merger of two galaxies, you can estimate by how much this dynamical process grew the black hole mass. Now, for this particular black hole, the dominant feature is actually cosmic strings, cold cosmic strings. Now, this is not true for all black holes, and it's important to actually really quantify this in much more detail with at least theoretically and in the future also observationally. So based on figures like this, you see that the growth of the black hole is rather smooth. So we imagine that galaxies are able to feed black holes with gas. Now the next question is, and we'll be very quick, what is the effect of the black hole on feeding itself? Now here I just want you to compare these two panels. Here it's a simulation of a redshift 6 quasar, of a redshift 6 galaxy with and without a quasar in it. This is density and this is temperature. Now look here at the effect that the AGN has on its environment. Look at the temperatures that shoot up to very high values. So the black hole itself is heating and giving energy to its environment. And gas that is hot and energetic will have a hard time being accreted to the black hole. And in fact, when we look at the black hole growth as a function of redshift, we see first an early happy growth. But eventually here at redshift about 6.5 or so, the energy given by the black hole to its environment will stop it from growing at high rates. So what I just want to highlight here is that we should keep in mind that black holes may be endangering their own growth, at high redshift at least, when galaxies were small. Now, in the last minute, look at this part of the curve here. You see it has a very constant gradient. This is because the simulation had a clear if. If the inflow rate of gas is larger than the end-inflow rate, put it at the end-inflow rate. Is this a good choice? Well, in just one slide, I would like to advocate that super-Reddington accretion may actually exist, or at least be useful. Remember that super-Reddington accretion is different from super-Reddington luminosity. When the accretion rate is highly super-Reddington, radiation can be trapped and modify your accretion disk. And for instance, in slim disks, the relationship between luminosity and accretion rate in units of Eddington both becomes logarithmic rather than linear. So you have very high accretion rates without having very high luminosities. So you can read this as a low effective radio efficiency in the equation that I showed you earlier on that may help black holes at high redshift grow a bit faster. And I think at this point I will just put up my summary and just remind you that it's important to think of black hole formation as an integral physical path that is important to understand the growth of black holes. And we should try to estimate accurately how black holes are fed and what is their feedback effect on their galaxies if we really want to understand the highest redshift quasars. Thank you. This one?
Did you get it from the simulation?
Yes, yes.
So from your simulation?
No, this is a simulation by Gillian Bellovary, Alison Brooks, and myself.
Or is this cosmological?
It's a cosmological simulation.
So that shows that the photos are being measured on
For this particular black hole, we have another black hole where you have mostly galaxy mergers doing the effort, but for statistically, out of 3 galaxies, 2 are mostly fed by cold flows.
You said that you have also, in principle, you would be able to predict the absorption amounts. So I would be interested in your predictions whether the black holes are absorbed or not, because that might be, you might be able to measure.
Absolutely. I just thought of this talking to you, hearing you this morning, so let's stay tuned.